Hello, ladies and gentlemen, and welcome back. In this video, we're going to finish off our 2019 Galois paper with question number 4. A positive integer is digit balanced if each digit d, and d can be any digit between 0 and 9, appears at most d times. Okay, so then why bother considering 0? 0 would have to appear at most 0 times. Alright, that's weird. At most d times in the integer, for example, 13224, so 13,224 is digit balanced. 4 appears, it doesn't appear 5 times or more. 3 doesn't appear 4 times or more. 2 only appears twice, so not 3 times. Yeah, okay, that makes sense. But this one here is not, because 2 appears 3 times, whereas it should appear at most 2 times. Okay, so that's an interesting order. Written, light bulb, written. Explain why a digit balanced integer is not divisible by 10. Okay. Well, so this shouldn't be that bad. Oh, we're stuck on continuous mode again. Love it when that happens. Anyway, so there's a nice little divisibility rule for a number. Be a multiple of 10, it must end in a 0. Okay, but that means then we have at least one 0. So 0 appears so not at most 0 times. 0 appears at least one time. So our number cannot be digit balanced. Okay, not a bad write-up. Just very quick. You gotta end in a 0, but you can't have any zeros, so can't be digit balanced. Alright, B, the light bulb. How many 4-digit integers have all non-zero digits and are not digit balanced? Okay, so ignore the ones that have zeros. So only consider digits 1 through 9, because they said non-zero. All right, now there's 2 ways we might go about doing this. Okay, one thing we might do is just straight count the number of not digit balanced 4-digit numbers there are. Or another thing we can do, we can figure out how many 4-digit numbers there are that have non-zero digits and figure out how many of them are digit balanced and subtract that from the total. So there's 2 different approaches we could do. I don't know if one is going to be easier than the other. I think I'll probably start out trying to directly compute the number that are not digit balanced. But if that turns out to have too many cases, too difficult, it's hard for me to wrap my head around exactly how to count it, I might try the other approach, which is total number of 4-digit numbers minus not the thing they're asking you for, but the opposite, so the number of actually digit balanced 4-digit numbers. Okay. And so just with 4 digits and only 9 digits, there'd be 9 to the 4 total. And then the question is, well, how many do we have that are digit balanced and have no 0 digits? Okay, so that's an option. But let's try to get the non-digit balanced numbers. So to be not digit balanced. Of course, you don't actually have to explain any of this because it is a light bulb. If you just want to straight do the calculation, that's okay too. Yeah, as long as you're right, you'll get full marks. But let's see. To be not digit balanced, we need at least 2 1s, or at least 3 2s, or at least 4 3s, and so on, all the way up to at least 10 9s. Now, something like 10 9s isn't going to happen. We only have 4 digits. So with 4-digit numbers, we see, for example, we'll never have 5 4s or 6 fives. So that's not going to be too much of a problem for us. So that means we have just 3 cases. Actually, I don't know how much work we're going to have to do with these 3 cases, but so we could have 2 1s, or we could have 3 2s, or we could have 4 3s. Now, if you have 4 3s, you really only have this as an option. That's the only 4-digit number that's got 4 3s in it. But if I have 2 1s, if I sort of imagine a 4-digit number, as soon as I have 2 1s, it's not digit balanced. And that gives me options for what the other digits can be. And they could be any other sort of numbers. Any others at all. In fact, we could even have more 1s. So what's the best way to count this? I'll think about that for a moment. Same thing with 3 2s. We've got 4 digits. 3 of them have to be 2s, but I don't know exactly where that other digit's going to be and what it is going to be. So I think we're going to have to break this up into 2 cases. Actually having 4 2s, in which case there's only 1 number, or you have exactly 3 2s, in which case you have 4 choices as to where the non-2 goes. There's 1 case here, 1 case here, 4 choices, and then because it's not a 2, you can have 1, you can have 3, you can have all the way up to 9. You have 8 possibilities. So that gives me 32 options there. Okay? And I think we're going to have to break the 2 1s case up as well. So exactly 2 1s, exactly 3 1s, or exactly 4 1s. The 4 1s case, again, there's only 1 option. There should be 32 options for our 3 1s case. By the exact same reasoning. I've got 4 digits. 1 of them isn't a 1. So I've got 4 choices as to where to put that non-1. And then I have 8 digits that aren't 1 for it to be. So I get 2 choices there, and I multiply the number of options. Now when it comes to 2 1s, okay, I have 2 blank ones to take care of. Now, if you know a little bit of combinatorics, you might know that this is the answer here is going to be 4 choose 2, which is 6. But if not, you're more than welcome to sort of list out the possibilities. Okay, so those are the possibilities. Because we're not dealing with 0 digits, I don't have to worry about 0 being a lead digit. Okay? So there's 6 choices for where the 1s go. Okay, and then I've got to choose my other 2 digits, and they can't be 1s, otherwise we'd be in one of the other cases. So there's 8 choices for the first digit, and then 8 choices for the next digit. So that's 6 times 64, so that would be 384, I believe. Although we can quickly grab our calculator and check. 384. And that should do it. So the total they're looking for, 1 case with the 4 3s, 1 case with 4 2s, 1 case with 4 1s, 32 cases with 3 2s, 32 cases with 3 1s, and 384 cases with just 2 1s. And so we just add all those up. And so our answer should be 451. Okay? So, as I said, this isn't the only way we could try and approach the question. What we could do instead is sort of say, all right, the total number of 4-digit numbers that don't have any zeros is 9 to the power of 4, which is that 6,561? Yes, it is. Good for me. Okay, and instead we could subtract the ones that are digit balanced. Okay. Okay. But in order to do this, and the reason I'm now realizing that this method isn't the best is because you're going to have a lot more that you have to worry about. Okay? Do you have any 5s? Well, actually, it doesn't matter if you have 5s. It again only matters if you have too many 1s, too many 2s, or too many 3s. I think there probably is a way to do this, but I can't think of a cleaner way than just the few cases we had here. So I'm definitely saying that this will probably take too long. Now, if you actually bother to write it out, I want to move on to part C. Please leave a comment down below and give me the gist of it. Was it faster than what I did by computing the answer directly? Did you have any particular challenges? Were there a lot of cases? Were there very few cases? Let me know. But I'm going to move on to C part. Okay. Determine all positive integers k, for which there exists digit-balanced positive integers m and n, where m plus n is 10 to the k. And m and n have k digits. Okay, so we just want the k's. We don't want to know how many pairs m and n work or anything like that. What can we do here? Well, how do we make... I think we're going to have to look at the individual digits. And the only thing I really know is that m plus n is 10 to the k, and they're telling me they're k digits long. So maybe we could start off by saying, let m equal... I guess we should probably start at the end. A0, A1, for the 10 to the 1's digit and 10 to the 2's digit and so on, all the way up to a to the k minus 1, because they want k digits. So these are the digits here. Now when I add them, I should get well, they're telling me that I need to get 10 to the k. So 0, 0, 0, it just keeps going 0 and then another 1. Now, A and B, actually, none of these digits can be 0. We sort of, we know that they can't be 0 because otherwise you're not digit balanced. So we have 0 zeros because m and n are digit balanced. We don't really need to justify that much. So A0 plus B0, it can't be 0 plus 0, so this has got to be a 10, because it can't be 20. I guess we can say AI and BI are always between 1 and 9. So that means that AI plus BI is always between 2 and 18. So to carry a digit, we must have AI plus BI equal 10. So that tells me A0 plus B0 must be equal to 10. Now there's going to be lots of options that do that, but that does mean that then we get this 0 down here, and then we carry a 1. And so then carrying that 1 plus A1 plus B1 must be, well, it can't be 0, and it won't be enough to be 10. Or sorry, it won't be enough to be 20. Oh, good, it's doing that again. I don't know why Drawboard PDF started doing that a little while ago. Back to our question. Okay, let's say carry a digit. Okay. We can also see that AI plus BI plus 1 is between 3 and 19. So if you're going to carry a digit and get a 0, let's say to get a 0. And actually, that should be my reasoning up here. Not to carry a digit, but to get a 0. So to get a 0, you've got to get that, and then that means you carry a digit. But it looks like we're always going to carry a 1. So I guess we could write like this. So those two have to add to 10, and then we carry a 1, and we get another 10. So A1 plus B1 is 9, and that'll carry a 1. And so then that's got to be 10, so you'll carry a 1. So in fact, I guess we can say for I greater than 0, AI plus BI must be 9. And that continues, yeah, you'll still get to carry the 1 here from that 0, and that'll be a 10. Okay. So, what does that tell us? A0 plus B0 must be 10, A1 plus B1 must be 9. That's sort of it in terms of how these digits can be related, but now we've got to sort of deal with the fact that they've got to be digit balanced. So for example, AI can't be 0, so BI can't be 9. Right? Because if BI were 9, then AI would have to be 0 because they have to add up to 9. So neither of these numbers can have any 9s in them. Okay. And that sort of limits things because there is a limit to how big a digit balanced number can be. Right? At most you have 9 9s, 8 8s, 7 7s, all the way down to 1 1. So that means at most you have a 45 digit balanced number. Yeah. So there's that, but you get sort of this, and actually you get further pairings. If AI is 1, BI must be 8. We can have at most 1 1 in M, so at most 1 8 in N. And this sort of goes in you know, you can have at most 2 2s. What goes with 2 to make 9? 7. Okay, so let's yeah, but the A0 and the B0 are going to complicate things ever so slightly. So actually, let's ignore those for a moment. Although it might turn out to be that they've got to be 4 6 or 5 5 or one of these sort of middle pairs. I want to make some sort of a chart. Actually, let's just say M can have at most 1. No, I'm going to make a chart. I think it's just easier to lay out my information. M, sort of ignoring A0 for a moment. So you can have at most 1 1, and that means at most 1 8. You can have at most 2 2s, and therefore at most 2 7s. I know for a digit balanced number you could have at most 7 7s, but you need those 7s to pair up with 2s in N, and if N is also digit balanced, you're not going to have enough 2s. 3 3s means 3 6s, 4 4s means 4 5s. And that's sort of ignoring the A0. So this gives me a limit to how long M can be. It could be at most, I guess, 20, and then A0 21. So the number of digits is at most 21, and I think because we'll be able to spare a 5, this should work. Yeah. So I've proven I don't need to worry about more than 21. For any k, I think it should be any k, because 5, 5 would work. So for any k less than 21, we claim there is such a pair. And that would answer the question, because they want to know which k's, right? Not how many k's. Determine all positive k. I'm going to say all k's less than 21. And there is such a pair, m and n. Let's say construct as follows. Let's just be very careful. A0 and B0 should both be 5. That'll make a 10. And you'll notice we have a sort of a spare 5. You can have a fifth 5. I think that should work. And then so I guess what do we say? I know what I mean, but it's going to be hard to. The 5's there. Then I'm going to say put a 1 here and an 8 here. 2 2s, 7 7s, 3 3s. That'll be 6 6 6. 4 4s, 4 5s, but you'll notice now we have at most 5 5s here. We'll also get at most 5 5s here, so these are digit balanced. 3 3s again, 2 2s, and a 1. That'll do it. So there's a 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21 version of this. And so if you want anything less, so you can always just sort of chop wherever you want and say, all right, now this bit is the m I want and this bit is the n I want for a k of length 2, 4, 6, 8, 9. Okay, so there's my pattern. You've got to get the 5s there. And it doesn't have to be this, but there's my m. There's an m and an n, or sort of a pattern for making the mn's. So we could say something like make m and n by, we'll be fancy, we'll say truncating from the left, or trimming down from the left to the desired number of digits. Okay, these answers are clearly digit balanced, and we've also sort of explained why this is at most you can have. You can get 10 of those, 10 of those, and we've ditched a digit. 21 is the best you could do. Okay, and then there's an explicit example of 21, and we're saying you can just cut it wherever you want and read from the right, and you'll get an answer that you need. Okay, interesting little question there. I liked it. Yeah, I don't really think I have anything else to say about it. It was a nice Galois paper overall. I'm going to move on now to the 2019 Hypatia paper. If you're looking for more grade 10 level papers, more Galois contests, feel free to browse around. I have a number of them ready. You can try the contest for yourself, and then we can compare solutions. But until then, thank you guys so much for watching, and have a wonderful day.